So our last skill here in Learning Unit 5 on Equilibria has to do with shifting equilibria. And wow, oh, your head probably hurts from doing those equilibrium problems, solving those equilibrium problems. Those are tough problems. There's a lot to think about. There's a lot of steps to do, but it is one of the key skills that we are going to do in Gen Chem 2. And it has application in the next 2 learning units. So please make sure that you master that skill. All right, last little piece here is more qualitative, thinking about shifting equilibria. So conceptually, I want you to imagine that this is changing the teeter-totter. Remember, changing the teeter-totter has to do with, well, every reaction has a set point that it wants to be at. But if we're not at that teeter-totter, or we shift it away from where it wants to be, it's going to move to try to shift back. So conceptually, I want you to think about that. So how can we actually change a teeter-totter? Well, there's 2 general ways that we're going to talk about changing the position of a teeter-totter. We can change or affect the amounts of materials that we have, maybe products or reactants. Or we can think about changing the temperature or the pressure, remembering that we can change pressure by adjusting volume. This really only has a lot to do when we have gaseous species, but we're going to go through some examples of the ways that we can change equilibria. So we call this a disturbance, right? We're going to disturb an equilibrium, we're going to poke it, and then we're going to see what happens as it readjusts, okay? So we're going to disturb where we are at, and then we're going to allow it to readjust to get back to where it wants to be. And so your reaction is going to do so in one of 2 ways. It's either going to shift to the right and make more products, or it's going to shift to the left and make more reactants. Okay, so what we're going to do here is try to understand which way it's going to shift. And I've got a simple analogy here to help you think about how that's going to happen. This shifting of equilibria is called Le Chateliers Principle. So that's how you say that name, Le Chateliers Principle. And it basically just says when an equilibrium is disturbed, when you change the concentration or the amounts of materials, when you change pressure or volume or temperature, it's going to shift to try to restore equilibrium. And this is a really important concept. It doesn't mean you get back to the same equilibrium values. Rather, you get to a new set of values that still equal K. So mathematically, there's lots of numbers that I could put in here that will equal whatever my equilibrium constant is. It's not that it has to be exactly what those numbers are. I can change those numbers and still have it equal the equilibrium constant. Both of those situations would be at equilibrium. So we're going to go through a problem in class that's going to allow us to see that. So highlighting many sets of values for these equilibrium concentrations can mathematically equal our K. It's not one set of numbers, okay? All right, so how do we think about this qualitatively rather than quantitatively? I want you to think about a push-pull analogy. When we talk about a pull analogy, we're going to be talking about removing a reagent, and what's going to happen is the equilibrium is going to shift to the same side. It's going to pull it close. I almost want you to imagine like a curtain rod that's got curtains that are on there that we've got a drawstring on either side. And if I pull on that drawstring, it's going to move the curtains over that way. I'll shift my equilibrium to the right. If I pull on the other side, it's going to shift in the opposite direction. So we're going to use this pull-push analogy. Again, pulling is when we remove a reagent. Pushing means adding a reagent. We push something into our system or we pull something out of our system. This is going to allow us to have a very simple way to think about how different things will shift an equilibrium. So again, if we add a reactant, it's going to push the equilibrium to the right. But if we remove a reactant, it's going to pull it back to the left, making more reactant. Okay, so we're going to think about some examples here just with this very simple system here. So we've got this system where we've got PCl3 plus Cl2 gas makes PCl5. Okay, we don't even really need to use the equilibrium constant that we have here, but here's how you'd write that equilibrium expression and the value for the equilibrium constant. So let's think about what's happening here if we qualitatively change these amounts. All right, I'm going to add PCl5. This means I'm going to push in a product. So I'm pushing on the right side, so things are going to go to the left. This means my equilibrium is going to shift left. What about if I add PCl3? So this means I'm pushing in a reactant. In this case, I'm going to shift to the right. So I'm pushing on the left side. I'm pushing on my reactant side, so I shift away from that. What about adding Cl2? This is going to be the same thing here. I'm going to push in a reactant, so it's going to shift right again. PCl3 and Cl2 are both reactants, so that's going to push and make more products. Removing, this is a pull. So if I remove Cl2, I'm going to pull out a reactant. And that means that I am going to shift left. I'm pulling on my reactant side, so I'm going to pull stuff towards it. I shift to the left. Removing PCl3, well, that's also a reactant. So pull out a reactant, I'm going to shift left. Removing PCl5, that's pulling out a product. And so now I'm going to shift right. It's as simple as a push-pull analogy. Temperature. So how does temperature affect things? Well, remember, we can have reactions that are either exothermic or endothermic. Okay? And what I want you to think about when we're talking about changing temperature is treating heat as a reagent. Notice I didn't say reactant because heat could either be on the reactant side or the product side. So if we've got this equation, for example, in this equation, we've got it written where heat is a product, so that is an exothermic reaction. So if I'm adding heat, that means I'm pushing in a product. My equilibrium is going to shift left. I push it to the left. If I cool down my reaction, I remove heat, okay? Then I'm going to pull it out, so my reaction is going to get pulled to the right. What about if we had an endothermic reaction? Notice here, all I did was reverse this reaction and it becomes endothermic, right? So if we've got an endothermic reaction, that means that heat is a reactant. Now if I add heat, I'm pushing in a reactant, that's going to push my reaction to the right. I'm going to make more product. However, if I were to cool down an endothermic reaction, I would pull out this heat, meaning that I would pull the reaction left. I would actually make more reactant here. Okay, so that's how we can think about heat. What about pressure changes? Okay, this has to do with thinking about giving gas molecules enough space to kind of hang out and live, right? They don't want to be cramped up next to one another. So if we think about changes in pressure, there's 3 ways that we can change pressure. We could change the amount. Well, that really just plays into what we had on our last couple of slides, changing the amount. We can add an inert gas. Well, inert gases are not part of our equilibrium expression, so there's no effect. This is really a trick question, and I can almost guarantee you're going to see a quiz question on it. If you add an inert gas, there's no effect on the equilibrium. There's no shifting that happens. All right, so what's the only thing that will affect things? That will be changing the volume, okay? So we can change the volume. If we're not adding in more gas, the only way to really change the pressure is to change the volume, right? Remember that volume and pressure are inversely proportional. If I want to increase the pressure, that means I need to decrease the volume. These are inversely proportional, okay? So what this really means is we are going to shift to the side of the equilibrium that's going to allow our molecules to have more space, okay? So let's imagine that I increase my pressure because I decrease my volume. My equilibrium will shift to the side that has fewer molecules. So you have to count gas molecules. What if I actually gave more room to my molecules? Well, then my equilibrium can shift to the side where there's more molecules. Sort of a trick question again. If you have equal numbers of gas molecules on both sides, pressure and volume changes will have no effect. So lots of qualitative questions that you'll see that allow us to think about shifting equilibrium with pressure, volume, temperature, and quantity. Wow, those are all the things that are in PV equals nRT, right? So all of this is really related to gas equilibria. All right, one more sort of variation on a theme. Remember, we saw in Unit 1 this equation that allowed us to measure the vapor pressure of gases at different temperatures, and we could use that to get the enthalpy of vaporization. Well, in our last unit, our kinetics unit, we could measure the temperature dependence of rate constants and use that to get an activation energy. We've got one more flavor of this equation, which looks at the temperature dependence of equilibrium constants. And we can use that to get the enthalpy of a reaction. So remember, with these equations, all that you really need to know is how to solve for the unknown variable. So now we've got three flavors of them relating to pressure temperature relations, rate constant temperature relations, and now equilibrium constant temperature relations. So just know how to use this equation and how to solve for an unknown variable. See, so much of this comes down to algebra.